Chapter 16, Section 3, the electric field. So we have talked about electric force in Section 2, and we talked about electric charge in Section 1. Now we're going to add on electric field. Just know that when you do the next chapter, whatever we learn in this chapter, we build on in the next chapter. We just keep adding to it. So it's going to be important that you understand this chapter so that you can apply and move forward in the next one. An electric field is a region where an electric force on a test charge can be detected. Electric field, we use a capital E as its symbol, and it's measured in newtons per coulomb. Newtons per coulomb. And the direction of this electric field is in the direction of the electric force that would be exerted on a small positive test charge. It's important that you realize when we talk about electric fields, we're always going to refer to this point as a small positive test charge, not a negative one, but positive.
An electric field is a region of space around a charged object in which a stationary charged object experiences an electric force because of its charge. The electric field at a point is defined as the electric force that would be exerted on a small positive charge, called a test charge, located at that point.
So test charge, that's what we're calling this.
The electric force, like any other force, is a vector quantity. The strength of the electric field at a point is defined as the magnitude of the force acting on the test charge divided by the charge of the test particle, which is always positive. The direction of the electric field at a point is defined as the direction of the electric force that would be exerted on the test charge.
Okay, so you can see the capital Q there. You've got your little q, which is your test charges. Both of them are positive. And then it shows you that big yellow line is your electric field, and we'll end up talking more about it, if not today, definitely in the first section of Chapter 17. For the two positive ones, why is your E pointing to the right? It's repelling, and for the other one, it's pointing towards the negative charge because of attraction. So you have an equation there. Electric field is F electric over Q sub 0. Write that down if you don't already have it. In this case, it's just a test charge. They call it naught or original. It can mean multiple things. Now we have another equation here. Your electric field strength, that's your capital E, due to a point charge. You've got Coulomb's constant again. What is the value for Coulomb's constant? 8.99 times 10 to the 9th. What about the little q? Charge producing the field, what is the value for it going to be? As far as units go. Coulombs, and then distance is going to be in meters. So E is going to be, once you look at all of these units, it's going to be in newtons over coulombs. So there's another equation for you to write down. The next video that we're going to look at is going to have a sample problem. It's going to kind of go through all of this within the video, and then we're actually going to work it out within the PowerPoint itself.
Small charges, one positive and one negative. Using the superposition principle, you can calculate the net electric field at any point.
Do y'all remember the superposition principle?
No. That's the one where basically if you add up all the vectors, you get the force.
Yep. Adding up vectors.
Choose a point P directly above Q1. First, calculate the electric field produced by each charge at point P, and then find the vector sum of these fields.
Point P. What is that supposed to be? What is point P? That's our positive test charge. Okay? So it is a positive test charge, and we're going to look at it through here, but what kind of vector do you think is going to go between P and Q1?
Propulsion.
It's going to repel in a vertical direction. And then for Q2, it's going to attract along that dotted line between P and Q2. So you can see we're going to end up dealing with components again before this is over with.
The electric field at a point is the electric force that a small positive charge would experience at that location. The magnitude of the electric force exerted on the test charge by Q1 is given by Coulomb's law. Q1 and Q0 are both positive, so they repel each other. Since Q2 is negative, the force it exerts on Q0 is attractive. The strength of the electric field at point P produced by Q1 is the force divided by the charge Q0. The strength of the electric field produced by Q2 is found by an identical procedure. The forces on the test charge have been replaced by electric fields at a point in space. Now the x and y components of each electric field can be found separately. Then the components can be added to give the x and y components of the net electric field, which are shown here. These components can be added by drawing.
Oh, that was good. Okay, it doesn't matter. We're going to work it out anyways. So let's go work it out. It's within the PowerPoint. So again, this is the same sample problem that was given in the earlier example. They give us values for Q1 and Q2 here. So you can write those down. It gives you the distance. We're working with a 3, 4, 5 triangle here. Okay. And then you've got your test value, the point P, and it shows you where it's at along the y-axis and the distance it is from Q1. And it wants us to find the electric field, strength at P. And it's telling you, apply the principle of superposition. First, calculate your electric field produced by each charge individually at point P, and then add these fields together as vectors. And it kind of showed you, if we go back again in the previous section, electric force, that was Kc, and then you had Q1, Q2 over R squared. How is the equation going to be different when we talk about electric field strength? Right. Okay. So you've got your K that you're working with, same one. You have your one charge you're working with, and then your distance, whatever that is going to be squared. So I'm just trying to point out to you the difference between the two different equations. They are representing something just a little bit different. So there's your calculations you get for E1 and E2. This is your electric field strength as far as Q1 and Q2 go. And it shows their distance from your test charge. Now if we look at this, again, we had Q1 here. Oh, sorry. I'll just repeat the last part. We just looked at electric field strength, and we're going to have to break E2 into its components. I know. So much for saying all that. So they've got it drawn for you one way here. We've just added on to this where the resultant is actually going to lie. So we're going to have to figure out the components of the resultant force. So for E1, we said that was directly along your y-axis. So the entire electric field strength that we found for it, that's going to stay true. And then for E2, we have to break it up into X and Y components. Any questions on the math portion that's done here? Because they gave us the angle. That's not something that we had to solve for, but they did give us the angle.
Where does the angle fit in on the triangle?
Where does the angle fit in?
Left corner.
He says the left corner. This?
Yes.
Theta. And they're given theta as 53.1 degrees. Okay? So that angle was given to us at the very beginning. So going back to this, you have your X and Y components. The math's been done there. It's supposed to be simple math based on what we've already done before. And now they've taken all the values that you've gotten and they're trying to calculate the total electric field strength. So they're adding up all of our x-axis electric field strength, the y-axis. You can see the two values that you've gotten there. What are we going to end up doing with that? Pythagorean theorem. So when I look at that and I go back to this drawing right here, what we looked at earlier, we said, okay, it's probably going to be, the resultant's going to be over there in quadrant 1 somewhere. So we're trying to find out what that resultant is now that we've got all of our components in the x and y, and we can figure out, okay, x, y, we have them, go back and do the Pythagorean theorem. I don't know why it cut it out, but that's what I was explaining as I was drawing it. So now they've calculated E total for you. A squared plus B squared equals C squared. They've broken it all down, plugged in the numbers, and there's your electric field strength. This is around our test charge point P. What else do we have to include? Got to include direction. On the next slide, they're going to include direction, so they're going to use the tangent function, throw in your x and y components, and find that the...
Did you have all the components at this point? You can use any of them.
Yes. Yes. So they found the angle to be 66 degrees. Is that 66 degrees going to be from the x-axis or from the y-axis?
From the X.
From the x. And they give you a little picture right there too. It is off of the x-axis. Any questions on the math? Yeah.
When we were finding the
This right here is saying just make sure you evaluate your answer. Did you actually come up with an angle and electric field strength value that makes sense for the charges that are represented? And this one does. Electric field lines. This will probably be one of the easier things that we do all year. I'm glad, y'all should be glad anyways that that's the case. The number of field lines is proportional to your electric field strength, and these lines are tangent to the electric field vector at any point. What does tangent mean?
touching.
Okay? Touching but moving more like a perpendicular type manner. Okay? So they're showing you positive charge, that's your plus, negative is your minus. The yellow line that you see there is your electric field vector. And then electric field lines, you can see that these are lines. And again, they do show arrows, and those arrows, we're going to show you some examples of how do you use them.
Lines are a way of visualizing electric fields. For an isolated positive charge, the lines originate on the charge and continue to infinity. For an isolated negative charge, the lines originate at infinity and terminate on the charge. When two...
Don't ask. We'll start it again.
Electric field lines are a way of visualizing electric fields. For an isolated positive charge, the lines originate on the charge and continue to infinity. For an isolated negative charge, the lines originate at infinity and terminate on the charge. When two or more charges are present, the field lines still obey the same simple rule. The number of lines leaving a positive charge or terminating on a negative charge is proportional to the magnitude of the charge. The third and last rule is that the lines of the same field cannot cross each other.
So make sure you highlight those three rules. The two things that they mentioned earlier. If you have a positive charge, how do the lines move? Towards or away?
Away.
Okay? So positive charges, they move away. Negative charges, they move towards. The number of field lines you have, it says, is going to be proportional to whatever charge you've got. Notice in this last example, a +2 and a -2 charge, they've drawn 1, 2, 3, 4, 5, 6. They've drawn 12 lines off of each one. Okay? Because those charges are the same, I don't care if you would have drawn 3 and 3, 6 and 6, 2 and 2, 4 and 4, 20 and 20. As long as, because they're the same charge, they have to have the same number of field lines. What if one would have been, say, what if that would have been +4 and this would have been a -1? How many field lines do you want to draw?
You do 8 on the 4.
Okay, do 8 on this one. Which way are they going to go?
Toward
the one and away.
Okay,
Out.
so 1, 2, 3, 4, 5, 6, 7, 8. And what about the -1?
We'll give it 2.
Which direction?
straight towards it.
Okay, straight towards it. So
Would that make
when you say
contact
towards
with
it, what are you meaning towards it?
Towards the 4. Right.
If they're positive, they move away from the charge. If they're negative, what do?
They only move
Towards itself.
Oh, okay.
Towards itself. How many lines?
1. 2. 2.
If we did 8 off the +4, you got to have how many?
2. It's double.
2. 2 off of this one. So we'll connect
So is it by a factor?
2 of those. Okay? Because it is going to move towards the negative. Yeah. Just make it says proportional. It's going to be by a factor of. Okay.
So it's not always just double. If
No.
it's 2, it was double.
Huh?
Like if there was a +2, it'd be double. But
Right.
anyway,
Right.
Since a 4, like you do
Right. It's 4
12,
times. Yeah.
You need 3.
Right. That's it. Yep. At this stage of the game, how many ever lines you pick to initially set your proportion on is up to you.
There'd be a point in the game where we
Equal and opposite charges, the number of lines that begin at the positive charge is equal to the number of lines that terminate on the negative charge. Near the charges, the electric field lines are nearly radial. The electric field is strongest in the region between the charges, which is indicated by the high density of field lines. For 2 positive charges, the field lines originate on each charge and continue to infinity. Again, close to either charge, the lines are nearly radial. In this case, the electric field has a minimum in the region between the charges, which is indicated by the low density of field lines. If both charges are negative, the representation of the field will be similar, except that the lines will originate at infinity and terminate on the charges. The field created by a negative particle and a positive particle with double the charge resembles that of the equal and opposite charges, except that only half the lines originating from the positive particle terminate on the negative charge.
So again, it shows them starting and then how they terminate if the charges are not equal.
If the negative particle has twice the charge of the positive particle, the field would be similar. All you have to do is replace the direction of the field lines.
So, talking about conductors themselves in electrostatic equilibrium, your electric field is 0 everywhere inside a conductor. Okay? Electric field is 0 everywhere inside of a conductor. Why would that be?
Because it doesn't happen. Oh wait,
Charge flows really easy through conductors, right? So electric field is going to be 0. Any excess charge on an isolated conductor resides entirely on the conductor's outer surface. So it's important. So any isolated excess charge on a conductor is going to be on its outer surface. The electric field just outside a charged conductor is perpendicular to the conductor surface. So just outside of a charged conductor, the electric field is perpendicular. And for irregularly shaped conductors, the charge tends to accumulate at sharp points. And so what they're saying there, now think about it, usually whenever you get shocked, isn't it your fingertips that is where it usually happens? It's not like your shoulder hitting something. I mean, it's going to be something that's sharp, kind of pointy. So one of the examples that they give here is it kind of looks like this. You've got, that's not good enough. Looks almost like an oval. Okay, you've got this right here. You've got your negative charges that want to accumulate there at your sharp points. Going back to the one before it, saying the electric field is going to be perpendicular to the conductor surface, and you're going to look like this. Those electric fields are going to be perpendicular to the surface. So make sure you know those 4 things talking about electrostatic equilibrium.